Our first speaker on the stage is Nemanja Milosevic, Assistant Professor at the Department of Mathematics and Informatics, University of Novi Sad. Nemanja will be presenting Beyond Supervised Learning with Zero-Shot Vision. In this session, he will explore the principles of zero-shot image classification, which enables models to recognize unseen objects without prior examples. He will discuss techniques like CLIP, current challenges, and real-world applications in areas such as image retrieval and autonomous vehicles. Please welcome Nemanja Milosevic to the stage.
Thank you. Welcome, everybody. I'm so happy to see so many of you, and I hope you will have fun. We have a very interesting topic today. Before we start, just a short introduction. My name is Nemanja. I have a PhD in computer science, and I work as an assistant professor at University of Novi Sad, where I teach deep learning related courses. I'm also head of data analytics at Boston startup Autometric, which does ADAS for autonomous vehicles. From recently, I'm very happy to say I'm also NVIDIA Deep Learning Institute certified mentor, which is a nice community for sharing talks like this one, and always check what free courses are available, and can you get courses from your institution, just as a reminder. So, agenda for today, we will talk a little bit about supervised learning, which I believe you are all familiar with, some of its limitations and let's say things that can be improved. We will talk a little bit about new frontiers in zero-shot learning and how you can use it today, with one specific example of text and image-based model, OpenAI Clip, and its variations. We will see about that, and I will show you some examples in the end, so it's easy for you to start using these models from today. Okay, so first, a refresher about supervised learning. So as you know, deep learning models need a lot of data to have decent performance, let's say, and in most, let's say, computer vision applications, you would want to have image data sets or video data sets with a lot of labeled data, good labeled data. In this scenario, models learn by making predictions on images, and we can check how well they work by checking the ground truth or labels. Now, the space which the labels provide is range of possibilities that the model can predict, right? So it cannot predict something that isn't in the training set. There is no deeper understanding of labels. So let me give you a short example. If you had a computer vision model and you train it to recognize, let's say, some objects that are red, some objects that are blue, but later you want to expand your, let's say, classes, or expand your data set to train some new models which are again red or blue, you would have to add another class. There is no deeper understanding of what does the red group mean, what does the blue group mean in this example. So this is something that we can make a little better by using models like CLIP and in general zero-shot learning. On the bottom you can see a very traditional AlexNet architecture. It's a bit old now, but it's still very relevant because it's similar to most of the, let's say, state-of-the-art deep learning computer vision models of today. You have some convolutional layers in the beginning, you have some dense layers or fully connected layers at the end, and the important part is the last layer. You can see here we have the fully connected layer 8, which has 1,000 classes because this model was trained on ImageNet, and if we want to add another class, it's very difficult in this architecture to add it without changing the actual architecture. Continuing, what are the issues with this approach? So, as we mentioned, it's impractical in some real-world scenarios. You will always have this problem that you want to add something, and it's difficult to do in traditional models. Another problem is no general or transferable knowledge, which means that model knows to recognize those classes, but nothing in between. There is no fuzziness between the classes. It cannot learn to generalize knowledge based on the data that we gave it. Another issue is if you are working with annotations in your work, you know that they can be wrong, they can be very difficult to obtain, they don't exist most of the time, and these are just some of the examples from the ImageNet. There is a really good website called Label Errors where you can explore what data in ImageNet has been labeled bad. So a lot of issues like this can prevent the model from having high performance. With that introduction, we can now talk a little bit about zero-shot learning. Now, this term is not some specific model or specific, let's say, architecture. It's more a way how you set it up, how you set up the training process. There is also, you might have heard about one-shot or few-shot learning, but most of them work in the similar way. The main goal is to be able to predict labels or to predict classes which do not exist in the training set. Now, how can you do that? You can do that by not actually having labels like you usually have, but you would rely on some auxiliary knowledge, we call it, to make the predictions on the data. Now, what is this auxiliary knowledge? It can be a lot of things. There is no like single definition what it is. In most, let's say, state-of-the-art models of today, we are talking about embeddings. So imagine the same architecture that we had a couple of slides ago, AlexNet, but instead of having 1,000 classes at the end or one vector of length 1,000 that is the output of the model, you would have some embedding dimension that you would define, and the model would output not the probabilities, but it would output the actual vector which you can work with in different ways. Another benefit of this approach is that we can skip using the explicit annotations, and the model will learn better what is the implicit things about the labels, and it will have more general knowledge. So if you trained it on, for example, recognition, to come back to our first example, if you had example of training it on red trees like in the autumn and green trees in the summer, and then you want to train it on red balls and green balls, it would learn a little bit what red means and what is the differential between the red classes and the other classes. So that's the power of this approach, and it is very good when you combine it with large language models, which we will cover now. Okay, so how can we use zero-shot learning? Oftentimes, we don't want to start training the model from scratch. We don't want to have this output space, output vector to be completely, let's say, trained from scratch, because it will be very difficult for model to learn what we actually mean by some of the labels. That is why oftentimes in zero-shot learning we use transfer learning. So that means that we do not want to start training the models from scratch on some, let's say, random embeddings of our classes, but we want to have actually some smarter way to do that and to help the model learn quicker and better. So one idea that comes naturally from this is, can we use large language model sequence embeddings to replace the explicit classes in our model? And the answer is yes. So how do you do classification in this scenario? So imagine a model where the output is some embedding, which is also the embedding from some text model. Then you can define classes like sentences or words, and you can just do a similarity search between what the model outputted and what are the classes that you defined by text. So that is a very powerful way of thinking about this problem. So we are talking a lot about embedding, so just to go a little bit more into detail. So if we want to use zero-shot learning, we can use some of the already available, let's say, pre-trained models and their embeddings like BERT or Word2Vec or others. And also another nice thing is that we can use also pre-trained on ImageNet usually visual models which can also give us embeddings of images. We can also use autoencoders, which are very good to obtain, especially variational autoencoders, that are very good to compress the data and give us some representation of the input data. In this case, it's images that we can use to then, in combination with the output of the textual models, to do the classification and other tasks we will mention later. So one trick, or the main trick of the zero-shot learning is, okay, we have this image model, it gives us some embedding. We have this large language model, it gives us some embedding. How can we make that, how can we combine them? And the trick is to use joint embedding space. That means the both models will share during training. They will share same embedding space. And we will, in the loss function, penalize them if the image text pair, which is used for training, has a different representation from textual part and the visual part of the model. That is the main trick of the zero-shot learning training. So when we talk about joint embedding space, it obviously allows us, like we said, to have multimodal models. In this case, and when we talk about clip and general in computer vision, we will always combine image models or video models, sequences of images, with textual models. That allows us to specify labels as sentences or prompts, and that allows us also to have feature embeddings both from the visual part and the textual part, and to train with that. What is the joint embedding space? Just to formalize it a little bit, it is a normalized high-dimensional space which both these parts of the model share, both the visual and the textual part, and that is used to later do the searches, right? So how do we train these types of models? There is this concept called contrastive learning. Contrastive learning is not something new. It has been there for quite some time, but the main idea is how to align those embeddings, right? How can we align embeddings from the textual model and from the visual model? And the answer is we can use contrastive learning, which is basically telling the model during training that we want to minimize the distance in this high-dimensional space between the, let's say, image embedding and textual embedding from the same sample, from the same training sample, and we want to maximize the distance from other samples. So we can take image from one sample and text from other samples, and we want to maximize that distance during training. There is different ways how you can select which ones or where to maximize. You can do random sampling, just take some other examples. So that's a little bit too much into details, but the idea in principle is very simple. So we just want to, in this space, minimize the distance between the same class, let's say, representations, and maximize between different classes. With this idea in mind, we can train both the textual and the visual part in parallel or side by side. There is also research about that we can use just the negative part. You can search for it. It's called negative deep learning, where you don't even have the positive pairs. You only have the negative pairs, and by having a lot of negative pairs, model learns to have the representation. If you tell it in which directions not to go, in the end it will end up close to where it would end up if you just told it where to go. So it's a very interesting approach, which is similar to what we are describing here. Okay, a little bit about CLIP. CLIP is one of the, let's say, most popular models that uses zero-shot learning. CLIP is short for contrastive language image pre-training, which, when you know now what is contrastive, what is language image, what means pre-training, it's very easy to understand what it wants to do. So on the images, you can see how training works. So we have some image encoder, we have some text encoder. The training data is pairs of images and text, which is easily obtained from the internet, or you can build the data set yourself. And the idea that both of these parts of the CLIP model will give us some feature embedding, the textual part from the text and the image part from the image. Then we can do scalar product and see what is the difference between these two. And we want to minimize the distance on the diagonal and maximize the distance on the other fields. How can we then, when we train it like this, how to use it later to predict or to classify images? Basically, we create labels by specifying it with text. So different prompts will be different label. One label is one prompt. And then we give it an image. We give it these labels. And then the textual part of the model will create embeddings from the labels. The image part of the model will create embedding of the image. And we do a similarity search. The class which has the biggest similarity with the image embedding is the, let's say, most probable class. And that's it. So how does this look, let's say, in two-dimensional space, which is a simplification? So we have an image, and we have a text pair. You see two dogs running across a frosty field. So these 2 points in this high-dimensional embedding space should be close to one another. And we have some other textual embeddings. We have some other image embeddings, and they should be far apart from these two, right? So in this example, how would we train it? So image-text pairs. So every image is described with some description. So for training, we will talk a little bit about this later, but the training data sets that are used for CLIP is from the old times, let's say, when in web pages you had that alt text, which was supposed to be if the browser cannot load the image for some reason, there is some description of the image. So that is one way how you can obtain image-text pairs, and if you scrape the internet. So that is what has been used in training of CLIP. We will talk a little bit later about some of the known data sets. But the idea on the right is again the same. We have the textual embeddings, we have the visual embeddings, and we want to have, when we do the scalar product, we want to have the small distance between same pairs and large distance between varying pairs. So where can you use these types of models? Obviously, you can use them for classification, for image classification. We encode the labels with the textual part. We encode the images with the image encoder, which can be, for example, a visual transformer. And then we can do similarity search and ranking. One problem with this approach is that if you think about how ranking works in general, if you don't specify the correct, it will always choose some label. If you don't specify some label that you expect actually there is in the image. There is no limitation what you can write there. It's the same problem as in traditional image classification model if you just take the highest probability. So if you have some probability threshold that you want to check, like model confidence, here it would actually be distance or similarity score, which we can use to see are the vectors actually similar or they are really far apart. It's just some check that you have to do to be safe that the model actually predicted something and that it isn't just noise, right? So it's the same problem as traditional models, but just something to be careful about. This approach works also really well with object detection. If we split the image into grids of smaller patches, it's not very efficient, but it can work really nice. So these patches, if we compare them again with the sequence embeddings from the classes, we can get what is the similarity, which is basically the confidence, and we can deduce where the object is in the image. Again, not very efficient, but it can work really well without any retraining. One other use case, which is very useful, is text-to-image search. So you know that there is a lot of image data that is not easily searchable. You probably have features on your phones that will allow you to search through your gallery. Chances are they are using something like this. So How does it work? Without the image input, we can just take the sequence embedding from the textual part of the model and do a comparison against the whole data set of images. And then we can rank them by similarity again to find what is the most similar image or image embedding to the textual embedding which you provided by specifying the text. This concept is called content-based image retrieval. It's becoming very popular. It can work offline. It can work really fast. And basically, it allows us to perform textual queries against data sets of images, which is a very powerful feature that we can do, and that is not easily doable with older, let's say, traditional computer vision models. Another bonus use case is image generation. So we can use the clip architecture to specify some prompt and for it to generate the image which will be really similar to that prompt that we gave it. And one very nice example is a model called DALL-E, which is also from OpenAI, which uses most of the clip architecture. A little bit about data sets. So, like we said, okay, to train clip, we need image and text pairs. So OpenAI used roughly 400 million pairs to train the original model. There are now larger data sets. OpenClip is fully open source implementation of Clip. You can find it on GitHub. These two data sets, Lion 2B and Lion 5B, are obtained by scraping the internet. The first one has 2 billion images, second one has 5 billion images, and you can use them for non-commercial, for academic research. You can use them to train OpenClip. There are other implementations or variations of the clip architecture, like NVClip from NVIDIA, CClip from Google, Glip from Microsoft, and others. But the nice thing is they are all available in the Hugging Face Transformers library. And we don't have a lot of time, but let me just show you a few examples how it works. So on NVIDIA's, you can use their new NIM, neural inference Docker images to quickly play with Clip. And you can see here we provided some images and we provided some labels, or we asked the model which image above shows a warehouse, and you can see on the image 3 it says 100% I'm sure this is a warehouse because of that keyword. Another example, this is running on our Serbian AI platform. This is from Hugging Face library. This is the base model with patch size of 32 from OpenAI, and you can see it's just a few lines of code to actually run it. You basically give it image and you define classes by saying prompts. So we have two classes, a photo of a cat, photo of a dog, and that's it. It will give us probabilities or similarity scores, and you can see it works really well. Similar example is for Google's implementation, CGlip, which also works in same way. You specify image, you specify classes, and it will work without any issue. And the last example is for object detection. Again, with Hugging Face Transformers library, there is a pipeline called zero-shot object detection, which you can use. Again, you specify classes, you specify image, and you will get the bounding boxes where the objects are. Now you see it's not perfect. There is no NMS like in YOLO models, so there is some overlapping bounding boxes. But consider it's not actually trained. You can specify any labels, and you can easily see why it is very, very useful. So that's it. I hope I motivated you to try these types of models. They are very powerful. And that's it. If you have any questions, I will be around, or we have, I think, 7 minutes for questions, which is great. So thank you for your attention. Any questions?
Thank you for your talk. So this might be too detailed, but I'm wondering, what kind of loss function are you using? Contrastive.
So for the contrastive learning, you can use some distance measure that you want to, again, minimize between the actual image and label in the sample. So you can use Euclidean distance, you can use cosine similarity, you can use things like that, and you try to, the trick is when you try to minimize, when you try to maximize, there is two components to the loss function. It's not a traditional loss function, let's say, so you have to have those two parts, but any similarity or distance function would work. Mostly used is cosine similarity because it's really fast to calculate, but you can use other distance functions.
Cool, thanks.
Thank you for the question. Any other questions?
So thank you very much for the talk. First of all, I just wondered how many images do you need to train this network? So I remember a use case in a textile factory, and we had just like 10,000, let's say, undamaged products and just 20 ones which were damaged. How many images do you need so the system understands the concept between like damaged and non-damaged products? So how many images will it take?
It's hard to say without actually looking at the images. I would say in general less than you would need for a traditional model. Because you will start from, if you start from something like Lion, it's trained on 5 billion images, so it knows a lot of things, and if you want to just fine-tune it on your specific example, I don't think you need a lot of data to actually train it for your specific use case. Again, it really depends on what is in the images, how distinguishable they are, but I would say in general, these models, especially when you start and use transfer learning, you can get away with not having a lot of data.
Thank you very much.
Thank you. Any other questions? That's it. Thank you again for your attention.